Good, okay. So let's move on to the next part then. So we've got about 20 minutes or so, I think that'll be enough, okay? We noticed last time, actually, has anybody managed to copy down the probability distribution we had earlier, or yesterday? So could you read out, so I think we had 0, 1, 2, 3, 4. So this is the number of siblings, right? Yeah. Okay. What's the probability of picking someone with no siblings? Okay, and then one sibling? And then two siblings? And three siblings? 4 siblings? 5? 6? And everything else is 0. Okay. Now, could you for me, so x in this case, my random variable, also when you're dealing with probability distributions, always say what x represents, okay? So x in this case represents the number of siblings, so always write that down. Okay, so x represents the number of siblings, okay? So this is your outcome, this is the probability. Now, what if I wanted to have a closer look and see what does this actually look like, okay? So what does this probability distribution actually look like? Well, one of the most effective ways that I can do that is simply by graphing it, okay? Simply by graphing it. So can I give you 3 minutes? Can you draw this graph for me? Can you draw me this graph? So it's literally just going to be a bar chart, okay? Along the y-axis, you're going to have the probability. And along the x-axis, you're going to have the outcome, okay? So basically, you want to draw something like this, okay? So 0, 1, 2, 3, 4, 5, 6, and 7. Yeah, okay, 7 plus. Okay, and along the y-axis, you're going to have the probability. So literally, all I want you to do is make me, or draw me, a probability distribution. Can you plot it on a graph for me? Quite sure where to start. You'd start here and say, well, okay, my outcome is 0. So that's what goes along my x-axis. I find 0 along my x-axis. And then I'd put my probability. That gives me the height which I need to draw. Okay, so my probability should be 0.53, 53%, right? So therefore, it should be about that high. Does that make sense? Okay, and then the next one would be about 27%. It's about that. Then 2 will be 7. 3 will be 7. 4 will be 0. 5 will be 7. And everything else will be 0. So you should effectively end up with something that looks like that, where the height of each bar corresponds to the probability. Yeah? Now you notice in this case the way which I'm drawing it. I'm drawing it as distinct bars. Why do you think I'm drawing it as distinct bars rather than all joined together? Good. So if it's not continuous, what is it? It's discrete. Okay. So because it's discrete, I can show that quite easily on here, just by drawing it as discrete bars, like there's gaps between the bars. Does that make sense? Yeah? So for example, I can interpret this, a value of 1.5, which is halfway between 1 and 2, doesn't have any height there. So therefore, the probability of getting somebody who has 1.5 is 0, because we know it can't happen. It's discrete. Yeah? Okay, good. So what do we call this? So when we draw the graph of a discrete random variable, we call this a probability mass function. Okay? So probability mass function, or you can abbreviate that to a PMF if you want. A probability mass function is just simply a way of drawing the graph, or maybe just writing the function, okay, of a discrete random variable, probability mass function. Now, interestingly, just because we will look at discrete random variables, okay, sorry, continuous random variables, the continuous case, so if I had a continuous random variable, and if I drew the graph of that, we would call that not a probability mass function, but a probability, does anybody know? Does anybody know? So a discrete random variable, the function is called a probability mass function. Does anybody know what we call the function of a continuous random variable? It's called a probability density function. Okay. And again, we could call that a PDF for short. Okay. So just be aware of the difference. Now, these two things literally do exactly the same thing. It says, you give me an outcome and I will find you the associated probability. If it's discrete, we call it a probability mass function. If it's continuous, we call it a probability density function. Okay? Does anybody know the difference between mass and density? Like, is anybody a physicist in here? Does anybody know the difference between mass and density? Good. Right, close to that. So mass in like real life is just how heavy something is. Just how heavy something is. So if I said to you that I have a kilo of feathers and a kilo of lead, which is heavier, what would you say? Right, good. So they're both the same because I said 1 kilogram of feathers and 1 kilogram of lead. So they're both the same. But intuitively, what did you want to say? The lead, right? Because in reality, the lead is much denser. In other words, you would need much more feathers to have 1 kilogram than you would lead. Okay, so if you had 1 kilogram of lead, I could probably put this on a table. If I had 1 kilogram of feathers, I'd probably need a whole room to fill that. Does that make sense? So in actual fact, density is like mass, but it takes into account how much of it you have. Okay, it's taking into account spatial volume as well. Okay, so just be aware of those differences. Probability mass function, probability density function, they're the same thing. Mass is to do with discrete, continuous is density. Okay? All right, fine, okay? Now, could you do this on here for me? Could you find the probability, so using this probability distribution, either this one or this one, could you find for me the probability that a random variable, x, is less than or equal to 2? So find for me the probability that you pick somebody at random and they have a sibling which is smaller than or less than 2, or the number of siblings they have. I agree. What do we get? 87%. Perfect. How do we work that out? Yep. Absolutely. Yeah. Exactly. So probability of x less than or equal to 2 literally means add together all of the outcomes which are smaller than or equal to 2. So add together the probabilities of all the outcomes that are smaller than or equal to 2. So that's the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2. So 53% plus 27% plus 7% gives you 87%. Okay? Now, what am I really doing there when I'm adding together consecutive probabilities? Does anybody know what we call that? We call it something beginning with C. We call it cumulative. We call it cumulative. Okay. So cumulative probabilities is when you add together lots of successive probabilities, one after the other. Okay, so probability that x is less than or equal to 2, for example, would be probability that x equals 0, plus probability that x equals 1, plus probability that x equals 2. So you're literally just adding together consecutive probabilities one after the other. Okay, we call that cumulative. Now, if you think, if I asked a similar question, if I asked what's the probability that x is greater than 2, could I use this cumulative idea to work that out? Absolutely. So if I want the probability that x is greater than 2, that would just simply be 1 minus the probability that x is less than or equal to 2. What do we call these two things? X is smaller than or equal to 2, x is greater than 2. What are those two things? Are you happy they're complements of each other? Yeah? These are complements of each other. They kind of go together. If you add this probability to this probability, you should get 1. So it's like exhaustive. Does that make sense? It's like heads, the complement probability would be tails. Okay? Getting a 3 on a dice, the complement probability would be getting all the other numbers on the dice. 1, 2, 5, 4, 5, and 6. Yeah? Okay? So the idea of a cumulative probability is actually really, really useful. Okay? Because it's just simply where you add together lots of successive probabilities one after the other. If you want to find the greater than situation, it's just 1 minus the cumulative situation. Okay? So because it's so useful, we give it its own special name. Okay? So if I was going to change this now, change this graph into a cumulative graph, In other words, add together all of the probabilities as you go along. Could you have a go at that for me? So let's change this to be the probability that x is smaller than or equal to x. Okay? Well, first off, you're going to get 53%. Okay? Because it's going to add together all the probabilities up to that point. What's the probability that's going to go here? 80%. Perfect. Because you're going to add together all the probabilities up to that point. What's the probability that's going to go here? 87%. Because again, you're going to add together all the probabilities up to that point. What's going to go here? 94%. What's going to go here? 94%. Because again, you're adding together 53, 27, 7, 7, and 0. What's going to go here? Yeah, 100%. Clearly, we just rounded at some point. And in fact, everything else is going to be 100%. So could you now have a go at drawing the cumulative probability graph for me? So literally, what's on the screen? You should get something that looks like that. All I'm literally doing is just plotting these heights now. Okay? So you can see that it should start off, everything over here should be 0, then it should ramp up, and everything else over here should be 100%. Okay? Now actually, instead of writing probability that x is less than or equal to some value, sometimes I might write it like this. Capital F. Okay? So capital F literally just means a cumulative function. So if I want the probability that x is less than or equal to some value, I can write that as f of x. Okay? So if I asked you, for example, what would the f of 3 be? What would that be? If I asked you for f of 3, what would that be? Yep. 94%. If I asked you for f of 5, what would that be? 100%. If I asked you for f of 1, what would that be? 80%. You happy? So if I write f of something, it literally means the cumulative probability function. It means add together all of the probabilities up until that point. Is that okay? So in this case, this thing here would be a cumulative distribution function. Cumulative distribution function. If you like, a CDF for short. So there you go. There's just a summary of the difference between a probability mass function and a cumulative distribution function. So a probability mass function literally just tells you the probability of an individual value. What's the probability that x is equal to 4? What's the probability that x is equal to 5? What's the probability that x is equal to 7? By the way, if you wanted to stick with this f notation, a capital letter F is the cumulative function, a lowercase letter f is the probability mass function. Okay? So lowercase f, probability mass function, capital letter F is the cumulative distribution function. So the cumulative distribution function is literally what happens if you add together lots of consecutive probabilities up until that point.